today. Yeah, so just to quickly recap of where we're at, we're still like on this topic 5, yeah. And you can tell that Taewan's spending a lot of time, I guess, like covering it because it's a very core part of the course. You know, you use this stuff for serviceability later on. You use it for columns later on. You're going to be finding the essentially like the moment capacity of concrete a lot. Or this will also carry through to any composite section that you do in the future, right? So I know I mentioned this last week, but I'm doing timber steel composites in my thesis, for example. So it's an example of why it's useful. So we're going to be covering, I guess, like these two kind of at the same time, singly and doubly reinforced sections. But T-beams, I'm just going to briefly run over because I'd actually prefer to run over an example because I understand we're at kind of different stages. There's some people who are actually second years doing this course, partly because I like told them to do it. And for those people, you haven't done steels yet, right? And steels covers the limit state design quite thoroughly. That's like the M star, stuff like that, V star, whatever. But that's quite new. So I'm actually going to run through an example. Hope it'll make more sense by then. But even for the steels people, this stuff isn't like redundant information because how we handle dead loads is going to be a little different in this course. We actually account for the self-weight of concrete, which we'll see in a bit. Whereas in steel, you don't really account for the self-weight of the steel. You would just call that part of the G or the dead load. Okay, cool. So, and one more thing I want to talk about. I'm not sure about like in my yaps whether I'm going to be able to cover the design steps thoroughly. What my plan is at the moment is I'll tack that part on to the start of week 7's one because it's essentially the same thing again, but what we're going to be doing instead is designing a beam from scratch. Like you don't know what dimensions we're gonna make it. So it's just like based on a loading scenario. Here's how big our beam is going to be. It's going to be similar to how steels felt towards the start when you were actually I guess throughout the whole course where you were like choosing on one steel what your section size should have been for the I-beam or whatever. Okay. So this is kind of a recap of last time. Again, last week I covered mostly uncracked and cracked reinforced concrete. And now we're going to be focusing on the ultimate stage, right? In particular, in purple here I've highlighted where the concrete's fucked beyond belief, essentially. And you're gonna have all sorts of things happening, like the tensile side of the neutral axis is gonna be completely gone for the concrete material, and the concrete material is gonna be behaving non-linearly, right? And the steel, you have to check whether it's actually yielded or not. So there's all these kind of material properties which are gonna, there's a lot in scope, but at the same time, it's gonna be really rewarding to do the questions because you derive every section yourself, and if you understand the method, you can apply it to any section that you see. Okay. Moment of inertia, the good news for you guys is we don't have to worry about the moment of inertia for the moment for the ultimate stage. Moment of inertia calculations are more to do with the crack stage and serviceability design a little later on. And yeah, so it'll look something like this, so I'll just get into it. So I mentioned some of these topics towards the, I guess like these are what we call the assumptions, the underlying assumptions of our engineer's beam theory. It's also a sprinkle of like Newton's first law and stuff like that, and third law probably. But these are the setup. This is how they, I guess, came up with the numbers in the standard in order to figure out the capacity of the beam and like how much loading it can take, right? So the first one is that when we look at, I should probably draw this, right? So that's the concrete and compression, right? And then we have stuff like the stress of the compressive bars and the tensile bars, things like this. You're going to get familiar with the fact that we're going to draw stress diagrams, and then we're going to convert the stress diagrams to force diagrams mapped out against the depth of the section, right? And the idea of this rule or assumption is that we can say that using Newton's first law, right? we can equate the compressive forces to the tensile forces, and that's how we're going to find certain values. In particular, we're gonna use that to find the depth of the neutral axis, right? So that's like one of those key skills that we're gonna apply, and you'll see what I mean in a bit. The other one is like the internal moment equaling the external moment. I guess this is kind of like Newton's third law with the free body diagram stuff. The idea is the internal moment is calculated using those forces I was talking about and then multiplying them by the lever arm to find the resultant moment within the stress diagram. And the external moment is found through looking at 1300 kind of concepts, the statics, what kind of loads are applied on the beam. We also take into account the difference between G and Q. So G is dead load, right? Q is live load. And and we take this kind of like worst case scenario combination of those concepts. And then we find what that peak moment is. So for simply supported beam on a bending moment diagram, in the middle is basically when you're gonna have the most positive bending, right? Assuming it's uniformly loaded, you know what I mean? Okay. And then this one is from, I think you see Taewon talking a lot about curvature. So curvature is just one part of engineers' beam theory, but the main idea is that there's a perfect bond between the steel and concrete. What that means is as the beam is like sagging or like deforming, the steel and the concrete will move like at the same rate, the same strain rate, essentially, right? So that's the idea that plane sections remain plane. And if we take any cut along this section, it's just going to be like a straight cut, I guess. Yeah. There's no like diagonal cuts that you ever take using engineer's beam theory, stuff like that, right? So you'll see how this all. So this is all very theoretical right now, and you'll see how this plays into how we derive everything. But does anyone have any questions so far? Firstly. So here's what I guess like all the diagrams look like next to each other. So here's the order that I like to draw everything in, because to me this makes the most sense. We draw the cross section, right? And that's where we consider the compressive concrete and everything under the neutral axis is cracked like that. We have our bars, so you're gonna find all sorts of different configurations, right, for the types of beams you'll have to derive. So you might have one layer of this compressive steel, and you might have one layer of this tensile steel, right? But you could also have two layers of tensile steel, you could have two layers of compressive steel, you could have 0 layers of compressive steel, you know what I mean? So every section is going to look a little different. You could also have a T-beam, which we'll be talking about in a bit, but yeah, the idea is we just learn the skills and you can apply it to any section, right, of reinforced concrete. Okay, so have you, like, how up to date are you guys with like lectures and all that? Have you started learning about what makes stage 3 of concrete stage 3, like the ultimate, like what's the definition of when it reaches ultimate stage and you can't like analyze it anymore? Because it's one simple rule, but it kind of flies under the radar.
Very end, right? At the failing point.
Yeah, so you're right. So on a material curve, right? Let's just look at concrete, right? It'd be that point, yeah? The stress strain. But what defines that point? Like how do we consistently know that point? Okay, I'll give it away. That point is where the strain is equal to 0.003. That's the rule in the Australian standards, right? So it actually does keep going, to be honest. So if you look at the curve, it'll go to 0.004, whatever. But we can't safely consider that portion. We cut it off at 0.003 and say that this defines our ultimate moment, right? So with that said, what we do is we always take the compressive strain as 0.003. We call this epsilon Cu. Epsilon Cu means a strain of the extreme compressive fiber in the ultimate stage, right? This is like if you take anything away from my yap here, just keep in mind this is the number you have to remember because you're gonna see it everywhere, right? When we're doing strength and the strength design for a concrete beam. Okay. The next thing, so I like to basically draw left to right, so section, then strain, then stress, right? Essentially, actually, to be honest, I think this is this. Yeah, I looked this up this morning. So the FC value is the maximum compressive strength, not the strength at the ultimate stage, right? Yeah, basically, this is a really cooked parabola, right? Agree? And because the compressive material properties are very non-linear, and we don't like dealing with parabolas, right? So what we do in the Australian standards is we turn it into a rectangular distributed load, or a uniformly distributed load, or like a uniform stress block. That's what we call it, right? Sorry, rectangular stress block. And you can see, based on how we can kind of transform this shape, it's going to be a bit shorter, so it doesn't fully reach the neutral axis. We don't actually consider, we don't really consider any of that in compression, if that makes sense. Yeah, any of that concrete in compression using this method, because we're trying to find the resultant force later, which is in the middle of a rectangular distributed load, right? We call this, let's do it in orange. We call this gamma dn, right? So dn is depth to neutral axis, right? Gamma is a reduction factor of some sort, right? And then the other dimension here, we said that FC was this entire, the maximum stress value here, right? So what we multiplied by is alpha 2. Alpha 2 is another reduction factor. So you should get familiar with which dimension we're talking about when we're referring to this rectangular stress block. Does anyone have any questions? Yeah.
Wait, for stress, would we want to exaggerate it?
Oh, I see what you mean. Yeah, I see what you mean. What they're trying to do is get the correct position. Right, so I might draw it on the board. So if we have a concrete section, and I've cut it and all that, and the load acting on it is a parabola, right? Looks like that. What we care about is trying to get the center of this stress block, right? Like the position of it, trying to get a very accurate magnitude. Yeah. And so we have to turn that into a rectangle, and it ends up looking like that. It's a bit shorter on that side. I see what you mean. In this step, we're just trying to get as accurate as possible. The position as accurate as possible, the magnitude as accurate as possible. When we do those conservative kind of approaches, they come in later steps. So you can't double up on how conservative you are, because it'll vastly under-exaggerate how strong the actual section is. Yeah. Does anyone else have any questions so far? I feel like this is very solemn kind of energy, very pensive. Is it like am I going too quick or anything, or? Okay. I'll just keep cooking, but please ask questions if you have any. Okay, so we just turn these into forces, right? How do we get a stress into a force? Mm-hmm. Oh, sorry. Yes. So we multiplied by the area, right? So okay, let's do the easy one. The easy one is the steel first, right? So to get the steel, we multiply it by which area? So if we're looking at the compressive steel, what area we care about? There's a name for it, yeah. I know what you're talking about there. Area above neutral axis. So we just care about the steel. So what kind of steel area are we looking at? The cross section of the entire rectangular. Very good. So it's just here, right? That's called AST. Oh, sorry, ASC for the compressive one, right? So that force we call CS, compressive steel force, right? What about the tensile one? TS is equal to FSY times, what are we multiplying? Which area are we multiplying it by? Very good. So you might have noticed here that I've done something slightly different for the compressive steel and the tensile steel. I've labeled the compressive steel as the stress of the compressive steel, and I've labeled the stress of the tensile steel as FSY. So does anyone want to crack it? Why that is? Why I've done it like that? So why have I labeled these differently for the tensile steel and the compressive steel in terms of how much stress they can take on?
Was this in steel mechanics?
No, this is
Steel mechanics. Steel mechanics.
steel structures, yeah. Kind of.
Do they fail differently?
I might draw the curve here. So I'll draw the curve on the left here, right? So we know that steel, it has uniform properties in tension and compression, right? So this is our stress strain graph. So let's just say this is on the tensile side. It doesn't really matter. That's the compressive side, right? What's this value here where it plateaus? Called? Sorry? Yes, we'll call it FSY, but it's the same thing. So that's called the yield strength, right? Okay, so the other notation I wrote was sigma CS, which means the stress of the compressive bars, right? Do you think that would be the same as FSY? Yes, very good. Basically, it might be somewhere here, or at least this is what we're assuming, right? What we're saying is that this rebar hasn't yielded. We're saying that we assume that the compressive steel hasn't yielded, and we assume that the tensile steel has yielded, right? Does anyone want to give a crack at what determines whether it's yielded or not?
Compression equals to tension.
Compression is equal to tension. Okay, let's focus on just the compressive bars, for example, right? How do you know whether it's reached that number, which is FSY? FSY is like you have a full bucket, basically, of water. Do you know what I mean? You can't fill any more water in that bucket. But sigma CS is like a half-filled bucket or partially filled bucket. So what determines how full the bucket is? You know what I mean? Yeah, exactly. Well, yeah, but how do we know that? You know what I mean? You guys are like edging the right answer. You know what I mean? It's about the strain. It's about the strain, right? Because if I strain something enough, it's gonna yield. That's the idea, right? So what we have to do, you'll see this properly in another step, is see how far away the bars are from the neutral axis. Right, so since the tensile bars are quite far from the neutral axis, here, right, we can assume that it's safely yielded. But since the compressive bars aren't as far, we assume it's not yielded, and then we check that assumption later. Does that make sense? There is kind of a loose guideline, I would say. I just made up these numbers like earlier today. There is a guideline of how far it needs to be away to be considered yielded. I would say starting from about 100 mil away from the neutral axis, you should definitely check. If it's like somewhere around 100 mil from the neutral axis, you should definitely check whether it's yielded or not. If it's like 200 or more, it's definitely yielded. right? And the depths of our sections, they can range anywhere from 600 mil to like a meter. Do you know what I mean? Yeah. And when we look at a section like this, you can generally assume the neutral axis is like top heavy, so it's weighted more towards the top. And so therefore, since our compressive bars aren't as far away from that area, it's probably not yielded, you know what I mean? But you have to check, because every section is different, right? Okay. Who else has any questions? Okay, we continue. Okay, so there's like these numbers, right? So we simplified the nonlinear behavior of concrete to a uniformly distributed load. That's the rectangular stress block method. And we use these formulas, right?
Wait, is this the same as the Whitney stress block?
Yeah, yeah, it's called Whitney. So these numbers, you can have them memorized eventually. And these values for FC that it gives you, they're generally from the table. You'll see like 25, 32, 40. You'll see these numbers come up a lot. And so you'll start seeing the same values for gamma and alpha 2 come up a lot, and you'll get familiar with them, right? But this is a very critical formula. And I might just, sorry, I'm just conscious of the time a little bit, but I do want to bring up a little yap I have. It's partially to do with my thesis, right? Which is why I'm like fucking yapping about it. But this paper, I'm doing my research thesis with Hamid, and he was the guy who used to teach steels last year before Brian took it. That's him there, and he gave me this paper. It's by Stephen Foster, right? And it's about finding the 5 factors in concrete and reinforced concrete design. And he actually came up with these fucking values. It's crazy. So he established these numbers. This paper was produced in 2015, and you'll see there was a revision of the concrete standards in 2018 where they adopted these values. And in your final exam practice papers, you'll notice that he gives you or at least the ones that I've found, there's 2017 practice papers, 2019, all that. Follow the ones that are after 2018, because otherwise there'll be a different set of numbers that they use because they changed the standards, right?
So sorry to interrupt.
Yeah, right.
Is this class happening?
This is like an unofficial class, but you can study in the corner or something if you want. Or is there something that are you missing a class
there
for?
was an announcement that I got that apparently there's going to be a casual position, serving event here. So I just presume I remember.
Yeah, I'm not too sure, man. Yeah. Yep. But anyway, sorry. Anyway, I want to show you the picture as well. He was at first year camp in 2018. He was the head of school, but he's graduated onto bigger things now, Faculty of Engineering or something like that. Anyway, yep. Okay, does anyone have any questions about the rectangular stress block method? Okay, so here's the general step-by-step. So we assume the tensile steel is yielded, compressive steel is not yielded for the reasons I was talking about before. The tensile steel will be further away, so it'll most likely be yielded, right? We calculate gamma and alpha 2. So these are from these formulas, right? And then we calculate the forces CC, CS, and TS. So let me show you how this all feeds into each other. So these two feed into the concrete compressive strength, concrete compressive force, right? The compressive steel not yielding, you can find the force of the compressive steel using that assumption, and you can find the force of the tensile steel using the fact that it has yielded, right? So if you look down here at CC, we basically multiply this axis by this axis, right? And then we have to multiply it by the width of the concrete. So what that looks like on a section is something like this, right? So that's the width. right? And we're converting this distributed load, or it's like a stress basically, converting that into like one force, essentially. That looks like that. Got it? Okay. Yeah, so I've explained TS, and CS is this, but there's a bit more complexity to this, because if the steel hasn't yielded, it essentially has like some more steps that you have to do, right? So you have to break down the stress formula into elastic modulus and strain, and then the strain uses a technique called similar triangles to determine it based on let me just show you. So here is the strain of the compressive steel, right? And we essentially compare these two triangles, right? We say that the slope is the same. And so using that information and the fact that this is dn, we can derive some expression for epsilon cs, right? Are we okay? Do we need a mental health break or anything? All right, I like it. Let's continue. Okay, so then we can calculate dn using that whole idea of compressive forces is equal to tensile forces, right? So yeah, it's force equilibrium. And then we check those assumptions and check whether the steel actually has yielded or hasn't yielded, right? If our assumptions are correct, so we're saying here that the strain of the compressive steel is less than the limit, so we can calculate the limit separately, and that the tensile steel strain is greater than that limit, well, it means that we've correctly proven our assumption. So it looks something like this on a material curve for steel, right? Yeah, so we say that one number is greater than, one number is, let me zoom in for you, Mary. One number's over here, and the others hit this point here, FSY, and it can't go any higher than FSY, right? Even if the strain continues like to over here. Yeah, so again, also for those of you who are like copying down on that, I've got a recording of this, I've got a Google Drive of my notes. I can also upload the annotated notes of after when I'm done, like with all the scribbling and yapping. Okay. I like to redraw the force diagram, but you don't have to. And then you label the lever arms right on the force diagram relative to dn, and that will help us take the sum of the moments. So it looks something along the lines of this, right? Compressive concrete, compressive steel, tensile steel, right? We literally take the sum of the moments about this point. We find these distances here. Right? And we add them up. So that resultant moment is like grouping together all the moments due to those forces, and that will be our capacity for our concrete beam, right? Is anyone okay with that? Or not okay with that, rather?
Like with step 3, like is it like C equals to CS or?
Yeah, it's CC plus CS is equal to TS. You know what I mean? So you group together the compressive forces together, which is the compressive steel and the concrete, right?
Yeah.
And then you equal that to the tensile steel on the other side of the equation, right? Okay, I'm gonna carry on. So next we check for ductility, right? So ductility has this equation. It's quite a simple one. This is probably the easiest step, but it's at the very end. We just check that the depth of the neutral axis, and then check its ratio with the depth to the outermost layer of steel. So usually this is DST, right? But yeah, it says DO because if you have multiple layers of tensile steel, it's the one that's the furthest away, right, from the compressive side. Yeah, so you just check this ratio is less than 0.36, in which case ductile failure happens, right, which is good because we want basically the beam to have a little bit of warning before the whole building collapses. If you have brittle failure, it might just like collapse without any warning, any deflections, stuff like that, and it's no good. You also have this region of kind of linear interpolation. So, sorry, I should mention that for the capacity reduction factor, which for those of you who have done steel, you'd be familiar with the capacity reduction factor. So this is for the moment capacity reduction factor. It can range between 0.65 and 0.85, right? And yeah, everything in between is a linear interpolation based on that ratio that we found with this equation. Yeah? No? Oh yeah, I'm going to assume that's a yes.
Could you explain the ductile failure again?
So basically, ductile failure is where there's enough like warning before something completely breaks. So we know that concrete's a brittle material, right? But when we reinforce it with steel, right, it gives it a little bit of a mixed property when it's a composite, section. And so this equation is simply just like a check of that ratio. A check of yeah, it's just checking like how much the steel actually affects that kind of failure mode, I guess. Right. To be honest, I don't know how they derived it, the dn over do,
Yeah.
but yeah, it's just kind of in the standards. So we call it.
What training terms like? So you want the concrete to show signs of cracking first, right?
Yeah. Cracking is kind of expected in concrete, right? But you'd rather it do that than completely break without, any cracking or notice.
Concrete to fail before the steel fails.
Yes, that's actually right. So the idea is if the steel, no, it's the other way around. If the steel yields first, it actually gives it that ductile property. But if the concrete fails first, what happens is the steel has to take on a load very quickly, like has to absorb the load very quickly, and then it actually undergoes something called fast fracture. If you've done material science, fast fracture is just like, if you've done steel structures as well, it's like in tension. Do you know how sometimes it can? It's like the snapping based on the net section, that kind of thing. So that happens if it's not a ductile failure. It's a brittle failure, basically. Oh yeah. Actually, yeah, that's probably the best way to explain it because you've done steels, right?
Yeah.
So in week 1 of steels or week 2 or whatever, you did tension design in steel. There's 2 failure modes, right?
Yeah.
There's yielding on the gross section and snapping on the on the net section. So you want it to yield, not snap. And in order to do that, you have to follow this kind of reinforcement ductility check.
Okay. So you want it to bend towards.
Yeah. So one role of compressive reinforcement is actually to give it more ductile properties and allow it to fail in that yielding mode.
Inshallah.
Yeah. All right, is everyone okay with that? Yeah. Okay, so I'm going to go over this part very quickly. It's basically an extension of what I've just been talking about. Look, if you can understand kind of what I was saying before, you'll be pretty set with the T-beam. There's not that many extra steps involved with T-beam. But yeah, the core of this week and the core of this course is just understanding how the ultimate moment works, because it's very abstract at the start when you're first learning it, but very applicable skill. It's very useful. Okay. So basically in this T-beam, this is based on a question that was in, I think it was question 5 of the workshop or something. No, it's question 4 of the workshop. It has no compressive reinforcement, but 2 layers of tensile reinforcement, right? So I've kind of just given steps of how to do it, like kind of theoretically. You do the exact same thing, and you first have to assume that the neutral axis is in the flange. So for those of you who aren't sure what flange is like the larger width kind of region. and web is the smaller width kind of region, right? So you assume the neutral axis is here, right? Or at least gamma dn falls within that region. And if it is, then you kind of just carry out your steps as usual. But if it's not, right, if gamma dn, right, actually this is gamma dn, it's a mistake. If gamma dn is actually greater than TF, it means that the concrete that is in compression follows this T shape, right? And of course, this is going to be aids to calculate. So there's two ways you can split it up. You can split it up like this, right? And derive two different expressions for it, right? But to be honest, I found that this way is the better way to split it up. So CF is the compressive force of the flange, and then CW is the compressive force of the web, right? And you can just follow my formulas through, solve for dn. And yeah, you might need to use the quadratic equation to find dn here. Okay. You do your steel yield assumptions, and you calculate mu the same way. Ductility, exact same way as well. Okay, let's do a question. Actually, did anyone have any questions about the T-beam or no? Okay, sorry, I went through that part really fast. Yeah, you're right. So something I mentioned before in my last yap was in a slab system, right? What happens is that the beams that look like that, they're poured in situ, so they're poured on site, and so the beams and the slabs are poured together, right? So all we're saying with the beam is that, okay, we can consider that this is the area of the beam, but in reality, it's actually a bit stronger because of the rigidity due to the slab assisting it and giving it additional strength. So this turns out to be a value we call BEF, right? The effective flange width, right? And so that shape ends up being a T-beam. So even though it's not the most optimal shape, you see it a lot in practice. And so they have to teach you it in this core concrete course because it's just everywhere, I guess, in structural design. Yeah. Yep.
Right, in cases like that, right, what determines the actual width of the flange?
The effective width of the flange?
Oh, no, it's okay. It was the effective width, okay.
Oh, yeah. So it's based on a formula. I can't remember off the top of my head, but it'll be in the standards. It just says this is how much it can grab from either side.
Yeah, okay.
Yeah.
Because I was wondering about the middle part.
Yeah, so when we analyze it, do we cut it straight down half?
No, you have to like calculate
Yeah, but like, oh,
yeah.
Yep.
Actually include the middle part.
And you'll find that this is called the depth of the slab as something as well. So that flange is actually part of the slab's geometry, right?
wait, that space in the middle, is that included in the TV?
No. We just look at that. I'm just giving you the overall like context, like the zoomed out view.
So that Tetris piece that you
Yeah.
highlighted,
Yeah.
is that equivalent to what you've shown above?
Yeah.
Okay.
Yeah. So like the reason they get you to design T-beams before you know where they slot in is because you're going to be designing slabs later. So they're telling you it without the context first,
Okay.
but it's actually where it's from.
So that's the red Tetris piece. Okay.
Yeah, exactly. Okay, we're going to go through an example. I'm going to try to go through this quickly because I'm conscious of the time. Okay, so what's the first thing we would do? Essentially, you can calculate the left-hand side first or the right-hand side. What I'm talking about is in the very end, we're going to have to do this big check called, this is the capacity check, right? This is where we're working towards. So I call this the left-hand side. That's the external loads, and the right-hand side is capacity reduction factor and capacity of the beam, right? So I'm going to do left-hand side first, and I'll teach you guys about the self-weight stuff, right? So essentially, the self-weight's a function of two things, right? The unit weight of concrete multiplied by the cross-sectional area, right? What we're doing is we're finding what this distributed load is per meter run. So if you look at like this, right? the unit weight of concrete is a three-dimensional property. It's essentially density multiplied by gravity. So it's just a constant multiplied by density, right? So you are actually told what the density is here. It's this, right? And we multiply it. Gravity is equal to 10 in this course, by the way. So we multiply it by 10. I forgot what the units are. Meters per second squared or something, right? For acceleration. Yeah, anyway, so that's shit, right? This area, we multiply it by this cross-sectional area in order to get essentially a one-dimensional distributed load, like that. Okay, that's what we're doing for this calculation. So we multiply it by these concrete section numbers. Specifically, it's these two. But do you see what I'm doing here in terms of the numbers? I'm converting it from mil to meters, because this is going to be 24 kilonewtons per meter, right? Oh, sorry, per meter cubed. And these are both going to be in meters. And so this is going to give us the self-weight per meter run, 8.832. Is anyone confused about that? I'm not getting any yeses or nos. So okay. The idea. Okay, let me tell you again about the load combos, right? So we'll slow down for a second. I'd rather get this part down for you guys first before I continue. So I'll do this part slow, okay? Okay. I think the rest of this lesson will be about the load combos and doing the left-hand side of the equation. Right. Okay. So essentially, what's G? Right. It's an easy question. Dead load. Very good. What's Q? Very good. So G, it's made up of two components. Can you guess what that is?
Self-weight and then the force.
Very good. We call it the dead load due to partitions, or GP. So what is GP based on the question that we were given here?
The one on the far.
P something 50.
That's PQ.
Oh, I can't read.
Yep.
It's this.
It's 5 plus.
Oh, that's so well.
Okay, so what's self-weight?
2400 times 10.
That's that's gamma C
Times 5.
area. So that's that number there, right? So that's the self-weight, agree?
Yeah.
Yeah. So the self-weight is this part, right? Okay, good. So what about the GP? What's the weight due to dead load due to partitions? 50, are you sure?
No, 50 is the point load.
50 is the point load.
Is it 13.832 plus 5?
Yeah, exactly. So basically what I'm trying to get at is GP is 5, right? Because GP is given, but it's only implied in the picture.
Oh, okay.
Yeah. So when you add them together, this gives you 13.832,
Yeah.
and that's the value we're going to be using for WG, right? Which is the distributed load, right?
And then Q.
Okay. So why have I drawn, like sometimes you might have seen me add these numbers together, but why have I drawn it with a comma? Like why have I written 1.2G, comma 1.5Q?
Case the y load acts opposite direction.
True?
Is it when you're thinking about the different columns?
Yes. So because we have a distributed load and a point load, they interact differently. So you can't just like blindly add them together. You can't just add together a distributed load and a point load, because that's just not how it works. So what we're saying with this load combination is we have to exaggerate everything which is a dead load by 1.2 and exaggerate everything which is a live load by 1.5. Do you know what I mean? Okay, another question. What kind of beam do we have here?
Cantilever.
where are the most moments, like where's the max moment on a cantilever?
Furthest away from the fixed. Very end. Furthest away from the fixed.
Which end?
Furthest electron.
So here is the max load, like highest bending moment. So if I was to jump up and down on like a diving board, you'd expect it to break at the very tip that I'm jumping at, right?
No, it should be the
Oh, it's
closest
just
one.
like the lowest.
It's at the rigid end, right? It's at the rigid connection. So generally, if we ignore the point load quickly, if we get a bending moment diagram, right, it'll look like that, right, for a distributed load. So on cantilever, it's always at the, it's always at the rigid end, right? So what we're trying to do is we're trying to find what the maximum moment is, right, at the support. Right? Okay, so we have to do that by comparing 1.35G and 1.2G plus, and 1.5Q, right? So let's start with the easy one. What we're saying in the case that we only consider the dead loads, right, is we don't have to look at the live load for now, right? Actually, what I might do is I will scratch that out, right? And then I can easily rub it out later, okay? So, but what are we actually looking at? We care about the bending moment, right? What is the bending moment caused by this uniformly distributed load on the support, on the rigid support? How do you calculate bending moment, firstly?
So point load distance.
Yes, but we don't have a point load. We have a distributed load.
Convert it.
Convert it, very good. Okay, so we have to find what the equivalent load is, right? Which is, okay, so remember that this value here was 13.832, right? Yeah, we multiplied by 3, so now we've got the force, right? Now what's the lever arm?
1.5 meters.
Yep, so what I'm going to do is I'm going to times it by 3 again and divide by 2.
Bang, like that.
But it's the same thing. Yeah. So that's how we get the dead load case, right? Dead load only. The other case, right? We can do a very similar thing, but we're going to multiply the dead load portion by 1.2. But now we have to add on, because the point load we have to consider, it's going to cause a bending moment in the same direction and further exacerbate this load, right? So we're going to add it on, right? We multiply it by 1.5, but how do we get it for a point load?
2.7 times the point load, which is 50.
Very good.
Wow.
So 50 times 2.7. It's 2.7 meters away from the wall. That's what we're saying, right? So of course, even without calculating this, you can kind of see that the dead and live case is going to be much bigger, right? And so that's the value we're going to run with for for this essentially. I really have to go, but I'm going to explain very briefly for the recording how to follow along for the rest of this. So now we finally draw our section, our strain, our stress, and our force, right? But you have to consider the fact that we're dealing with a cantilever, and so the tensile reinforcement is going to be on the top side, right? And the depth of the neutral axis will start from the bottom side, yeah? And so we carry through all our calculations just like this, etc. Forces are equal to each other. And then we have to check for the strain of the steel to make sure that it's yielded and our assumption is correct. We find the ultimate moment through taking the lever arms and converting the numbers. Ductility check at the very end. It's a ductile section, so the capacity is 0.85. We multiply it all together, and 277 is less than 354, which was our capacity. That's how we do the question. But yeah, sorry, I just ran that through in like 1 minute. But does everyone understand the left-hand side? Because that left-hand side is going to cause you a lot of problems. It even caused, I'd say, most of the people in my timber class, which is a fucking 4th year elective, a lot of problems. You know, you're never going to stop struggling with the load combination stuff, even though like on paper it's very easy. Just like make sure you understand it very deeply. Okay.
Thank you, Henry.